let's take a look at section 8.3. And this is the second part of 8.3 since we did cross-sectional volumes yesterday. Today we're going to do a style where we basically are rotating a circle about the axis. So you could think of it as cross-sectional area where a circle is involved. We will call it a disk. And it's just commonly referred to as disk. And then there's washer method as well. So let's first cover a disk method. You can notice here the formula. It says a limit as the partition P goes to 0, and that would be the width of this goes to 0, so that we get very, very thin disk. And I've got pi. This would be like an r squared, so pi r squared. There's that area of our cross section, and then times the thickness of the cross section. That all converts into the definition of an integral. The integral from a to b of pi r squared dx. And here's where we pick up that big R for outer radius. I'll use little r for washer. When we get to washer, we'll have a hole, and we'll talk about inside radius and outside radius. So big R, little r will come into play as well. That's the reason for the big R. Disk method, just let's kind of evolve with this disk method. So I have some function, right? That's plotted out. And in this case, we're going to be revolving about the x-axis from A to B. And as that revolves, you can imagine that it creates a circle, right? Because this acts as a pivot point. It's pivoting about the x-axis. So we get some distance here, some big R, and we can see that the radius changes as the function changes. And what we want to do is we could pick out one spot here and follow that as it gets revolved around. Well, how can I get this more accurate? I can make the thickness of a disk much thinner, or create more disk. And to create more disk, we want to take and create that thickness to go down to 0, or create infinitely many slabs of disk along here. And if I think about a disk, it's going to have a cross-sectional area of pi r squared, and then multiplied by its thickness, and that'll give me the volume of one disk. And if I take and integrate the volume of the disk, or accumulate and sum up all those volumes, we'll get the total volume. So let's just get one started here. We're going to revolve around the x-axis first, so everything will be in terms of x's. That'll be where we have our rotation about the x-axis. This will act as my r, and I can calculate the distance of that taking the point f of x up here minus, well, this would be the function y equals 0, which is the x-axis. So I could have top minus bottom, f of x minus 0, but there really wouldn't be a reason to write the 0. And example 1 says, find the volume of a solid generated when the region is bounded by y equals 3x minus x squared, and the x-axis is revolved about the x-axis. So we've got it graphed. I know this is my representative rectangle, which really generates a disk for me of, of that thickness. It get a little interesting trying to draw them in here, but this would be like the thickness of my circle. That is really not very circular, but that'll work. Here's the center. So this distance is that big R that we're talking about. You can see here a 3D model of what this would look like as it revolves about the x-axis. You'll notice the revolution indicator there. So graph that, we got it graphed. Express the radius for one disk in terms of x if we're working in dx, and then y if we're working in dy. Well, let's work in x. So I'm going to do top minus bottom, because that's how I get distance of the segment when I'm perpendicular to x. Top minus bottom. So that top function is 3x minus x squared, and then minus the x-axis, which is 0. I'm even going to indicate this function is y equals 0, right? So basically I get big R equals 3x minus x squared inside there. Using the disk method, let's integrate that. So what I want to do is volume equals pi. The integral, it looks to me like it's 0 to 3, so rather than proving that, I'm just going to grab those for now. And 3x minus x squared, quantity squared, times the thickness. And that thickness is this distance, which is on the x-axis, a horizontal distance. That would be a dx. We could integrate this out by hand, of course. I would have to expand this, so I'd have a 9x squared minus, if I multiply these two, I'd have a 3x cubed doubled, so a 6x cubed, I believe. And then last times last will give me a positive x to the 4th. Hopefully I did that right. Dx. And then we know we'd have to go in and do the integration. We could do this one by hand. It's more fun with calculator, but if I multiplied up, I'd have what? X cubed, so a 3x cubed would result in a derivative of 9x squared. Add a power, I'm up at a 4, so I have a minus 6/4, 3/2 x to the 4th. Check the derivative, that would give me 4 times 3 is 12, 12 divided by 2 is 6, x to the 3rd, that works. And this will be x to the 5th over 5. And then we'd want to evaluate it from 0 to 3. Plugging all that in, you will end up with 81 pi over 10. Perfect. Example number 2 is one. Ooh, I want to make sure I didn't have anything sitting below there. Nope, we're good. All right, example number 2. The region bounded by the y-axis and the graph y equals 1/8 x cubed, y equals 0, and y equals 8. So I've got a y equals 8, and x equals 0, and then we've got our function, the cubic function, is revolved about the y-axis, so we're spinning around the y-axis, aren't we? Find the volume of the resulting. So if you imagine, here's going to be our radius this time. It's going to be an r of y radius. And that's going to give us a disk kind of situated like so. You kind of see the edge of that disk. It has this for a thickness, doesn't it? And it would kind of fade in the background. And the thickness of my disk is dy. So I know I'm going to be working with y's. I also, in order to find r, I need right function minus left function, right? So the thickness we could describe as dy. And since we're going to be working in y's, we got to solve our equation for x. So I'd have 8y equals x cubed, or the cube root of 8y equaling x, which we could reduce one more way. Cube root of 8 is 2, and then y to the 1/3, I'm going to write it that way, equals my x. So now I'm satisfied with that equation. The radius of the disk will be right minus left, and let's see what we got underneath here. There it is. So I get 2y to the 1/3. You could say it's minus 0 for this particular equation, right? X equals 0. But that's still going to come back, obviously, to 2y to the 1/3. Using the disk method, I need to know my c equals 0, and my d, my top value, is 8, because my bounds also have to be in terms of y, don't they? Let's see what's underneath here. Revealing this, here's our formula we're going to follow. So I'm going to get volume equals pi, the integral from 0 to 8, because those have to be y's. I'm going to write y on there just to remind you that they are y values, of r squared, because we're building up. the cross-sectional area of our disk, right, which is a pi r squared area, and that's a 2y to the 1/3 squared multiplied by pi times the thickness dy. And that should get us volume, and then we're just accumulating the volume of all the little disks in there. All right, so we could do this by hand. I'm sure it'd be way fun. 0 to 8. Squaring this, I'm going to get 4y to the 2/3 dy. Might as well bring our 4 out front, make it easier on ourselves. 0 to 8, y to the 2/3 dy. Integration. We would have a y to the add 1, so 3, that would be 5/3 multiplied by 3/5. You know what? That's going to come out front with me. And then evaluated 0 to 8. So now I'm looking at 12 pi over 5, 8 going in, 8, it'll be a cube root, won't it? And then I need to take it to the 5th. I'm going to put the 5th on the outside of that, minus cube root of 0 to the 5th, obviously 0. Cube root of 8 is a 2. 2 to the 5th is 32. 32 times 12 pi over 5. A lovely number. I see there's an answer. Do we dare? I'm scared. I can buy it. Yeah, that looks good. 384 pi over 5. 12 pi times 2 to the 5th. We got it. We should have been super positive about that. All right. Washer method. Washer method is when we have a hole and we get two different volumes. I get an outer volume and an inner volume. And you know what? I would love to see, just the parentheses right like that, because all of that gets multiplied by thickness dx. So we know by addition and subtraction of integrals, we could generate our own integral here, and I could put a pi there and have minus, so that this generates the large outside volume of the entire solid, and then this generates the volume of the voided space, this white space, which in this case will really look like a cylinder, won't it? So I would have, this would be my small volume that gets removed from the large yellow volume. So if I pull that out, it leaves a hole. So shown in the region above is the x-axis, which is revolved above the x-axis. Oh, shown is the region above the x-axis. There we go. How about the beige area? And it's revolved about the x-axis, and you can see there's this definite void area, right? We've got open space. Anytime you have an open space with your volume of your axis of rotation, you're going to be talking about a washer method. Notice there's a distance between the region, the beige region, and the axis of rotation. That means washer method to us. The volume can be imagined to be created from an infinite number of infinitely thin washers, little washers, right? And there's a hole going through our solid. Awesome. So we're going to do example 3. The region bounded by the graphs, we have y equals 1/2 x squared plus 3. That looks like the saddle shape, doesn't it? The parabola. And then I have a function of 1/3 x plus 1, our linear function. And then we have vertical lines at x equals -2, x equals 3, giving us bounds on the left and the right. And we're revolving about the x-axis. So our representative washer will be the x, and I just leave this picture on there because one time I ended up with a pretty decent picture, and I've never erased it since. So I'm going to get rid of this because it doesn't need to be there. We can talk about big R and little r. I'm going to erase both of those. Big R and little r. Big R goes from the axis of rotation to the outermost function, and then little r will be axis of rotation to the inner function, the region that spans the void area. So we will definitely want to use washer method. Since there's a gap or a void space between the region and the axis of rotation, since we're working in dx, these will all be measured or written in terms of x. These will be x values, right? X equals a and x equals b. The thickness of the washer is dx, since the region is revolving about the x-axis. The outer radius is going to be the farthest function away, so 1/2 x squared plus 3, take away the axis of rotation, which is, in this case, 0. Axis of rotation. Now, today we are not moving our axis of rotation. It is stuck at either the x or the y axes. But we definitely will start moving them, and then it starts getting more interesting. So that's why I put the 0 in there. Little r is our inside function. So we're going to take 1/3 x plus 1, subtract the axis of rotation, minus 0. So obviously we don't need those, but I think it's good to have them there. We know, I guess this is our axis of rotation, isn't it? It's revolving about the x. So let's get into our integral, writing the integral. Volume equals, we need a pi and the integral. We're going from -2 over, what was this number? Was it x equals 3? Yep. This was an x equals -2 vertical line, and this was an x equals 3. So I'm integrating from -2 to 3. I need my big R squared minus my little r of x squared, multiplied by dx, of course. So let's put some functions in place here. Big R, that's going to be a 1/2 x squared plus 3 quantity squared minus little r. Notice the squaring is on big R, not the difference of these, but each individual radius. 1/3 x plus 1 quantity squared dx. I think we covered this stuff last year, but I believe it was at the very end of the year and it was a short year, so I'm thinking you guys don't have a lot of practice on it. That's what I'm left with, and that will definitely be a fun one to integrate by hand. So we would do it using calculator, and that calculator gets us to 269.508. Right? Let's see if there's any more. I don't have my notes with me. It looks like that's the end. I am going to create a Delta math assignment for you guys on this that will help provide a bit of videos as well for extra support if you want it. So you're going to be looking for Delta Math 8.3, let's call it B assignment. Okay, have a good day.